Bay Innovation Park in Ganesha, Bay Innovation Park in Gade Bagay, and STP Vasanta Innovation Park in Bekasi. By upholding three pillars of education that comprise education, research, and community service, Institut Teknologi Bandung will consistently produce excellent human resources for a better Indonesia. Established in 1920 with the name Technische Hogeschool, Institut Teknologi Bandung, or ITB for short, is the oldest technical university in Indonesia. Located in Bandung City, West Java, Indonesia, ITB now has 12 faculties or schools, with 49 bachelor study programs, 52 master's programs, 27 doctor's programs, and 2 professional programs. ITB's vision is to be an outstanding, distinguished, independent, and internationally recognized university that leads changes towards welfare improvement of Indonesian nations and the world.
It is great honor to meet all of you. I am Kadasa Suryadi, Rector of Institut Teknologi Bandung. Welcome to ITB. ITB has declared to move from research university toward entrepreneurial university. It is marked by 3 key performance indicators: excellent in teaching and learning, excellent in research, and excellent in innovation and entrepreneurship.
Excellence in teaching and learning's progress is marked with an accreditation that is earned on a continuous basis. 34 study programs of ITB have received accreditation from international accreditation boards. More international accreditation boards will follow. As one of Indonesia's centers of research, ITB has produced a wide range of research from 5 centers of excellence. These research projects result in excellent innovations that are expected to compete in national and international markets, which will certainly make an impact on the economy, improving it significantly. ITB creates innovation that departs from problems in industry and communities. Research is conducted in order to deliver the best solution that will enhance production quality and resource efficiency through support of technology. ITB also continues to collaborate and build synergy with the government. Industry, and other higher education institutions. This will lead to the creation of new technology. This new technology is expected to enhance the economic prosperity of Indonesia in general. One way to make this happen is through the development of science and technoparks in various locations. ITB Innovation Park in Ganesha, ITB Innovation Park in Gede Bage, and STP Vasanta Innovation Park in Bekasi. By upholding three pillars of education that comprise education, research, and community service, Institut Teknologi Bandung will consistently produce excellent human resources for a better Indonesia.
Moya for this lesson.
Mathematics Community and Algebra Research Group of Faculty of Mathematics and Science ITB proudly present Mathematics Webinar on September 30 until October 2, inviting international and competent speakers Artur Kornilowicz, PhD from University of Bialystok, Poland, Dr. Shakir Ali from Aligarh Muslim University, India, Professor Thomas Brzezinski from Swansea University, UK. Register yourself to this link. Live on Mathematics ITB YouTube channel. Mathematics Community and Algebra Research Group of Faculty of Mathematics and Science ITB proudly present Mathematics Webinar on September 30 until October 2, inviting international and competent speakers Artur Kornilowicz, PhD from University of Bialystok, Poland, Dr. Shakir Ali from Aligarh Muslim University, India, Professor Thomas Brzezinski from Swansea University, UK. Register yourself to this link. Live on Mathematics ITB YouTube channel.
Morning.
Established in 1920 with the name Technische Hogeschool, Institut Teknologi Bandung, or ITB for short, is the oldest technical university in Indonesia. Located in Bandung City, West Java, Indonesia, ITB now has 12 faculties or schools, with 49 bachelor study programs, 52 master's programs, 27 doctor's programs, and 2 professional programs. ITB's vision is to be an outstanding, distinguished, independent, and internationally recognized university that leads changes towards welfare improvement of Indonesian nations and the world.
It is great honor to meet all of you. I am Kadasa Suryadi, Rector of Institut Teknologi Bandung. Welcome to ITB. ITB has declared to move from research university toward entrepreneurial university. It is marked by 3 key performance indicators: excellent in teaching and learning, excellent in research, and excellent in innovation and entrepreneurship.
Excellence in teaching and learning's progress is marked with an accreditation that is earned on a continuous basis. 34 study programs of ITB have received accreditation from international accreditation boards. More international accreditation boards will follow. As one of Indonesia's centers of research, ITB has produced a wide range of research from 5 centers of excellence. These research projects result in excellent innovations that are expected to compete in national and international markets, which will certainly make an impact on the economy, improving it significantly. ITB creates innovation that departs from problems in industry and communities. Research is conducted in order to deliver the best solution that will enhance production quality and resource efficiency through support of technology. ITB also continues to collaborate and build synergy with the government. Industry, and other higher education institutions. This will lead to the creation of new technology. This new technology is expected to enhance the economic prosperity of Indonesia in general. One way to make this happen is through the development of
Hello, Professor Kornilowicz. Okay, yeah, still morning there, yeah. Okay, ladies and gentlemen, may I have your attention, please? Our algebra seminar is about to begin. During the seminar, we kindly ask your cooperation to turn your microphone off for the sake of conduciveness of the event. And if possible, please turn on your camera together with the virtual background that we will send in the chat box. Thank you. Okay. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. It is a great pleasure for us to welcome you all to the first day of the Algebra Seminar 2022. This event is conducted by the Algebra Research Group, Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung. I am Fitri Ferdania, will be the moderator of this event. First of all, let me welcome our honorable guest for today. Welcome, Professor Wahyu Srigutomo, as the Dean of the Faculty of Mathematics and Natural Sciences, ITB. Also welcome, Professor Puji Astuti Waluyo, as the head of the Algebra Research Group, ITB. And then, welcome to all our honorable lecturers, Professor Thomas Brzezinski from Swansea University, UK. Artur Kornilowicz, PhD from University of Bialystok, Poland. And Dr. Shakir Ali from Aligarh Muslim University, India. And also, our warm welcome to all the participants to this algebra seminar. Well, ladies and gentlemen, this algebra seminar that should be conducted virtually from September 30 until October 2 is aimed at enriching our knowledge in algebra and also to expanding the research network between researchers from all over the world. The speakers will deliver a series of 2 lectures for each topic. And for today, on day 1, the topic goes beyond introduction of interactive theorem proving MISR. This first topic will be delivered by Artur Kornilowicz, PhD from the University of Bialystok, Poland. And it is divided into 2 lectures. The first session, introduction of the interactive theorem proving, and in the second session, it is entitled by working with MISR. Whereas on the second day, the topic is differential operators in rings that will be delivered by Dr. Shakir Ali from Aligarh Muslim University, India. And last but not least, the last topic of this algebra seminar is entitled On Traces that will be given by Professor Thomas Brzezinski from Swansea University, UK. Also, the agenda of today's event is, firstly, we will have the welcoming speeches and 2 sessions of lectures delivered by Artur Kornilowicz, PhD from University of Bialystok, Poland, in which the sessions are separated by a break. Also, there will be Q&A session at the end of the second lecture. So, without any further ado, I would like to invite Professor Puji Astuti Waluyo as the head of Algebra Research Group, Faculty of Mathematics and Natural Sciences, ITB, to give her welcoming speech. So, to Professor Puji, you might take your time.
Thank you, Fitri. The honorable invited speaker, Artur Kornilowicz, PhD. The honorable our deans of Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung, Professor Wahyu Srigutomo, and dear all happy participants. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everybody. Good morning, Professor Kornilowicz.
Good afternoon, good morning.
Thank you. It is a pleasure welcoming all of you to this algebra seminar organized by our Algebra Research Group, Faculty of Mathematics and Natural Sciences, Institut Teknologi Bandung. I am delighted that our Algebra Research Group can organize this algebra seminar with prominent speakers. We hope to hold seminars like this more often to facilitate meetings among algebra experts and researchers and students to share knowledge expertise and experience, and also to build collaboration. For that, I would like to thank to the invited speaker, especially to who is in this meeting, Professor Artur Kornilowicz, PhD, and also Dr. Shakir Ali and Professor Thomas Brzezinski for their willingness to spend their valuable times and effort to share their knowledge, expertise, and experience with us. I hope that all participants can take maximum benefit from this seminar in increasing knowledge and building network. I also hope that this seminar will inspire participants to come up with new research ideas, get ideas for solving research problems that are being pursued, or form or enhance collaboration. Therefore, I hope that this activity will not end in this seminar, but it will be followed by further activities such as new research topics, research collaboration. In this opportunity, I would like to thank Dr. Kantina Rahmaputri and teams for this welcome organized seminar. And before I close my remarks, allow me to introduce our group, the Algebra Research Group of Institute Teknologi Bandung. Our group has 14 members, 10 of them with PhD degree, 3 members currently in their PhD program, and 1 member is still looking for scholarship. Our research interests concerning algebra and module theory, such as hereditary, prime, and semi-prime properties. Research in this area, including research in module theory using categorical approach, such as abelian, triangulated, and derived categories. We are also interested in linear algebra and metric theory. Topic in this area, including properties, bilinear, and indefinite inner product spaces. Our member also interested in the application of algebra structure in coding theory, cryptography, and DNA mutations. Recently, we have extended our interest to graph theory, to graph constructed from algebraic structure, and also trust. As a result of our interest, we are delighted for Professor Brzezinski kindly accepted our invitation to present his knowledge and experience on trust. And it is hoped that this seminar can increase the involvement of our group in research in that topic. Our member also passionate and enthusiastic in teaching of mathematics. So thank you, Professor Artur Kornilowicz, for your share in this seminar. Finally, allow me to close my speech with wishing you all have nice and fruitful seminar. Thank you very much for your attention. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Okay, thank you so much, Professor Pujastuti Waluyo, for the welcoming speech. And then we would like to invite Professor Wahyu Srigutomo as the Dean of the Faculty of Mathematics and Natural Sciences, ITB, to give his welcoming speech and also to officially open this algebra seminar. To Professor Wahyu, the time is yours.
Thank you very much, Fitri. Assalamualaikum warahmatullahi wabarakatuh. Good morning, good afternoon, and good evening to all ladies and gentlemen. First, I would like to thank Allah for giving His blessing so that we could hold this activity. Because of His mercy, we are sitting in this opening even in good health. And I would also like to express my sincere gratitude to Artur Kornilowicz, PhD, Dr. Shakir Ali, and Professor Thomas Brzezinski, who have been willing to give their talk at this seminar. And thank you also to all participants who set your valuable time for coming to this event. On this occasion, briefly, I would like to talk a little bit about our faculty. The Faculty of Mathematics and Natural Sciences has 15 research group, and one of them is the Algebra Research Group, led by Professor Puji Astuti here. The Algebra Research Group regularly invites speakers from abroad to strengthen the vision of ITB as a locally relevant and globally respected university. This time, they are holding a 3-day algebra seminar, and on the first day, the speaker is Dr. Artur, and then tomorrow afternoon will be Dr. Shakir Ali and Professor Thomas Brzezinski on the last day. On behalf of the faculty, I hope you can enjoy this seminar by sharing ideas and exchange questions and other fruitful discussion. I hope this event can go well smoothly, and officially I open this algebra seminar by saying Bismillah. Bismillahirrahmanirrahim. I open this seminar. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Thank you.
Thank you very much.
Thank you so much, Professor Wahyu, for your welcoming speech. So, as the event has been officially open, we would like to invite every participant to turn your camera on for the very first photo session. So, yeah, please also, if possible, to use the virtual background we have provided on the chat box. Okay. Okay, maybe I will wait for a couple of minutes so you can open your camera. Okay, maybe yeah, Siti Humaira, Dian Arista, Kamal, and all the participants, can you open your camera? Okay. Okay, we will take the photo. Maybe Dr. Gantina, can you help me to screenshot the screen?
Okay.
Okay.
On count of 3, 1, 2, 3. Okay. Let's see the result first. Okay, it's already good. Okay. Thank you, everyone.
Okay, thank you so much. Okay, so now we are going to the first lecture session. However, before going to the session, I would like to explain some technical points and rules for our seminar. The first one, this seminar is streamed via YouTube and is being recorded, but the detail for the link will be announced later. Every participant has to join the meeting for at least 5 minutes before the session starts. And for the sake of conduciveness of the event, every participant has to turn off their microphone, except if allowed. And then, if possible, please keep your camera on during the sessions and use the provided virtual background. And any questions can be written in the chat box or can be asked directly to the speaker by unmuting the microphone in the Q&A session. And last, the participants' display name, please should conform to institution-full name. Okay. So without any further ado, we're going to the first lecture session from Artur Kornilowicz, PhD, about the introduction of interactive theorem proving Miser. Professor Kornilowicz, yeah, can you hear me?
Yes, yes,
okay.
Yes.
Yeah, it is an honor for us to have you in this seminar. Thank you so much.
Thank you very much for warming, welcoming words. And
okay.
I would like to thank the whole institute, your faculty, your research algebra group for the invitation and for allowing me presenting the Miser project.
Yeah.
Thank you very much. I believe it is our first seminar, but not last. I am very open for next such events.
But maybe before we start, may I share your short CV, Professor?
Yes.
Yeah. Okay. So we will share the screen. Okay. So here it is. Artur Kornilowicz, PhD from University of Bialystok, Poland. He is now the Deputy Director of the Institute of Computer Science for Science, and also head of the Laboratory of Programming and Formal Methods. And also he is a member of Association of Miser Users, Polish Information Processing Society, and Polish Society of Logic and Philosophy of Sciences. His research interest goes beyond computer-oriented formalization of mathematics and also theory of abstract computer. And his newest research publication are synthetic semantic form of Miser articles, a new export of the Miser mathematical library, refining algebraic hierarchy in mathematical repository of Miser, and also enhancement of properties in Miser. Yeah, so that's an amazing record from Professor Kornilowicz. Personally, I'm very excited to hear your lecture because personally for me, Miser is a new thing. So let us hear about Miser from Professor Kornilowicz. So the time is yours, Professor.
Yeah, thank you very much. So as you can see, all my scientific life is Miser. And before I present the Miser project, let me say a few words about the beginnings of my story with Miser. So when I was a student of mathematics, I had to choose a supervisor and subject of my master thesis. I had no idea about the precise topic of my thesis, but I knew that I wanted to use computers for mathematics. And I was very fortunate because there was a laboratory of computer science at my institute. So I visited the head of the laboratory and said that I was interested in using computers for mathematics. And asked him if he would agree to be my supervisor. He agreed, but under one condition. He said that I can be your supervisor, but provided you would use the Miser system for the thesis. At that time, I didn't know what the Miser was, but I immediately agreed to it. And the story started. And it was in 1993, so almost 30 years ago. And what was important in this story is that the head of the laboratory was Andrzej Trybulec, the inventor of the MISAR system. So I was really very lucky at that time. So now let me start the presentation of the system. I will share my screen and present my slides. Can you see slides?
Yes.
Yes.
Okay. So the introduction to the interactive you're improving, and I will say about MISAR. So the plan of the presentation is as follows. After short introduction, I will present, and in introduction, I will tell about the key components and the key features of the MISAR project, the MISAR system. And then I will present the MISAR language in more detail, software of the MISAR project, and formalized mathematics, which is our journal in which we publish results of our formalizations. So the MISAR project started around 1973 as an attempt to reconstruct mathematical vocabulary in a computer-oriented environment. And as I said, it was invented by Andrzej Trybulec, one of the pioneers of computer-aided formal reasoning. And the main components of the project are a formal language for writing mathematical proofs, we call it MISAR language, a computer system for verifying the correctness of proofs, and the library of formalized mathematics. We call it MISAR Mathematical Library, MML in short. So we have three main components: language, software, and library. A few words about the language. The language is designed to be as close as possible to the mathematical vernacular. Of course, I will share many examples during this lecture. And the key idea behind this language is that it should be efficiently and effectively processable by computers, but also what is important for us, readable by mathematicians. So the language is a reconstruction of the language of traditional mathematics. It is a subset of standard English used in mathematical texts. It is based on declarative style of natural deduction. It is important feature. It is declarative. So our proofs looks very similar to traditional proofs, which we can find in mathematical papers. The language is open in the sense that users can introduce new words to the language and define new mathematical concepts. And we can define predicates, which represent relation between objects, like equality, membership, or other inclusion and other concepts. Types, which basically represent nouns like set, function, relation, group, ring, so on. Adjectives, we can efficiently process adjectives like emptiness, finite, one-to-one function, bijectivity, or so. Operations, like addition, subtraction, multiplication, and many other. And structures. I think that structures which can represent tuples would be, I think, the most interest for you because of your interest in algebra. Our language allows prefix, infix, postfix notations, like in traditional mathematics, and it allows overloading of symbols, So, for example, the same symbols like plus can be used to represent different notions like addition of numbers or addition of elements in groups or addition of vectors. Of course, overloading generates several issues which have to be solved during the verification process of documents. And the most important is disambiguation of meanings of symbols. So at first glance, when we see the string a plus b, we don't know what it means, whether it is addition of numbers or addition of vectors. So we have to look carefully to types of a and b, and then we can decide the precise meaning of the formula. The key features of the MISAR system are the MISAR verifier, the main program of the MISAR project, the verifier which verifies the correctness of proofs, works as a disprover. It means that when the verifier gets an inference to be verified, first it negates the formula and then tries to find a contradiction. And when the contradiction is found, then it means that the original formula is true and is accepted by the verifier. Otherwise, the MISAR reports errors and asked users to fill gaps to explain proof in more detail. The system uses the classical first-order logic, no higher order logic, but one exception, we support second-order free variables, which allows us to define, we call them schemes, for example, the scheme of induction or similar schemes over arbitrary predicates. The system uses natural deduction for doing proofs. There are several natural deduction approaches. We have chosen Jaśkowski style. Jaśkowski is Polish logician, mathematician. The system uses declarative style. I said it before. And I told that the system uses classical first-order logic, so we support classical logical connectives, negation, conjunction, disjunction, implication, equivalence, and quantifiers, existential and general quantifier. So at MISAR text, we can use all of these connectives, logical connectives and quantifiers. But internally in the system, we use a system of semantic correlates. Semantic correlates which are represented using only negation, conjunction, and general quantifier. So the original formulae are translated using standard Boolean formulae to our semantic correlates. And the third component is library. And some time ago, the Frank Wiedeik said that a good system without a library is useless. A good library for a bad system is still very interesting. So the library is what counts. So, and really we observe that our library is very important in our community, because we have many mathematical theorems completely verified by our system, and the content of library is used by other systems to represent mathematical knowledge over the internet. Our library is called MISAR Mathematical Library, and it is a collection of articles. It started in 1989, so more than 15 years after the MISAR was invented. At that time, the Tribulets decided to collect all written in the Mizar language papers and create one common library. The library is based on axioms of the Tarski-Grothendieck set theory, and it is a kind of Zermelo-Frankel set theory with some extra axioms about universes. At the beginning of the project, there were trials with other axiomatizations like proper classes and so, but finally the Tarski-Grothendieck was chosen, and still we use this one set theory as our axiomatization. The current official version of Mizar Mathematical Library includes 1,412 articles written by almost 300 authors from different countries around the world. In our library, we have over 13,000 of definitions, using almost 10,000 symbols, and we have 65,000, more than 65,000 of proven theorems, 891 schemes. Schemes are just theorems with second-order free variables, and more than 17 registrations, whatever registration means now. These are special formulae automatically processed by the Mizar verifier. And in MML, there are many various mathematical domains, articles on various mathematical domains. And so we have papers about set theory, logic, calculus, number theory, abstract algebra, groups, rings, algebras, topology, category theory, geometry, but also mathematical models of computations and many others. So I believe that the current content of the MML is also, or can be also suitable for your research, because of abstract algebra and these algebraic topics covered in the MML. Just a few words about initial files of our library. So we have one article, we call it hidden, where we defined primitives or of our system. And by primitives, I mean equality of objects, membership, and two types like object and set. In set theory, everything is set, so we have a set as a primitive type. Tarski is a Mizar paper when the axiomatization of Tarski-Grothendieck is formalized, and X-Bull 0, X-Bull 1 are basic are articles on basic operation on sets, and then we have articles about power set and Cartesian product of sets, operations on relations, functions, function between sets. And what is important, I believe, for you, we have the part of library on structures, algebraic structures, and the struct 0 is the root of all articles, and then we have many articles about different algebraic structures. I will show in examples later, of course. So the basic unit of library is Mizar article. So we prepare Mizar articles, and what the Mizar articles are. These are plain text files with the extension .mis, of course, written in the Mizar language. And in articles, authors can define new symbols, new mathematical concepts. And whenever such new symbol is needed, we can introduce them into vocabulary files. So these are, again, plain text files with .voc extension. And each Mizar article consists of two parts. The first part, we call it environment. It is simply a list of imports from database. So we can use previously defined notions, theorems, definitions, and we have to import into our new document. And then we have a proper text, which is a list of definitions, theorems, and lemmas, schemes, and other items. And processing of Mizar articles consists of 2 or 3 stages. So at the beginning, we call it accommodation process, which is just reading our environment and importing things from database into our article, and then the verification process where the article is verified for first syntactical correctness and then semantical correctness. And when the article is finished, we can export it to the whole library for future usage. And before I present the Mizar language in more detail and Mizar verifier, let me say about how connectives and quantifiers are represented. So we have a contradiction, with negation with keyword not, conjunction, ampersand, disjunction or implication represented by implies, equivalence by EFF, intent only if, and the general quantifier. So we use for variable x being type theta holds some formula alpha over the x. So we have for being holds, and existential quantifiers are represented by x such that, so x exists variable x being type theta such that alpha. And among all these connectives, we can see also we call them flex-array connectives, like flex-array conjunction and flex-array disjunction with 3 dots. So ampersand 3 dots. Ampersand is, let's say, long conjunction of formulae from alpha 1 to alpha n. So it is just to better understanding the next slides. Okay, so how we can define notions in Mizar articles. Let me start from predicates. So predicates represent the relations between objects, and it is an example when we define inclusion of 2 sets. So inside the definition block, we have definition end. Because we would like to define the inclusion between 2 sets, we take 2 arguments. So let x, y be set means that we have 2 arguments of our definitions, which are sets. Pred means that we are going to define new predicate. So there is a keyword. And marked in red color, we have x included in y. It is a place where author can define which symbols can be used to represent our new notions. So C equal is chosen as a symbol of inclusion. And we use the one left argument and one right argument as in traditional mathematical documents. So we have x included in y means another keyword. Tarski def3, it is a label of the definition. So whenever we want to refer to the properties of inclusion, we can use this label. So all notions are uniquely identified by these labels. And then we have we call definitions. Double colon, colon, colon are comments in Mizar. So colon, colon, please remember, these start the comments. So standard definition of inclusion for X being object holds if X belongs to X, capital X, then X belongs to Y. Right? I think it is readable. And when we define notions, we can also declare some properties. The properties are special constructions which which introduce some automation to reasoning. So maybe at this stage of it's not very important, but we have such possibility. I will tell more about it later. So we can define adjectives. For example, again, when we want to define what the emptiness of set means, again, inside the definition block, we take one argument, so let X be set. ATTR means we are going to define attribute or adjective. And again, X is empty, so it is a place where authors can decide about symbols, how we name our adjectives. So empty is a good name for emptiness, of course. So X is empty, what means that not exist X being object such that X belongs to capital X. So standard definition. And also we have another syntax for adjectives, but maybe later after break during we talk about later. Types are very important because we can define, of course, predicated adjectives are important as well, but using types you can define concepts like function, relation, group, and so on. And this is we have two kinds of types. We call them non-expandable and expandable, and the difference is quite important in a few minutes. So the first example defines the morphism between two objects in category. So let's take C be category and B be objects of C. Of course, these notions, I mean category and objects, have to be imported from database, from previous works. And for the moment, let's keep the permissive assumption. This is the second line, assume home. And mode is a keyword when we want to define mode or types, we use mode. And morphism of A and B is a new name for our notion because we are going to introduce type of morphism between objects. So it is, of course, a good name. And after this arrow, we have result type of the new notion. So the morphism of A and B, in the sense between objects A and B, is of course the morphism of category C. So this blue text is a result type of our morphism, and from this, Mizar automatically understands that every morphism of A and B is morphism in category. What means? Means that it is a special keyword to represent just defined notion. So in here, it represents morphism of A and B. So the morphism between objects A and B belongs to the home set to the set of all morphisms between A and B. Of course, home should be defined somewhere else. And now what is very important. In Mizar, types must be non-empty. Types non-empty means that we have to guarantee, I mean authors, have to prove that there exists at least one object of each type. So in this sense, types are non-empty, and this can be done, the proof of the existence. Yes, we have the new keyword existence and proof. So we have to prove that there exists some M being morphism of C, it is the result type of our definition, such that the definition holds. Yes, so we have to prove that there exists at least one morphism of C, which belongs to the set of all morphisms between A and B. But of course, in category, not always there exists morphism between all objects. And to prove that between our chosen A and B objects, there is some morphism. So here we can use our permissive assumption. So we come back to our assumption that this third line in definition. Assume home AB is not equal to empty. So this assumption was needed, was necessary to prove the existence condition. Okay, and another sort of types are expandable types, which means that the syntax is different. We use argument, mode, because we would like to define new type, and the permutation of X. And permutation of X is bijective function of X between the same set. So this permutation of X is kind of shortcut for long types. Long, I mean, using several adjectives like bijective function. So instead of writing bijective function of XX, we can write simply permutation of X. And the difference between non-expandable types and expandable types is in the second case, permutation of X is understood as a bijective function of X, but bijective function of X is understood as permutation as well. And in the first case, to use the property of morphism, I mean that it belongs to home set of A and B, we have to directly refer to the label of the definition. In the second, we don't need any reference, but in the first case, we need. In examples, maybe during exercises after break, we will discuss it more precisely. Okay. And operations. How to define operations? Again, we have definitional block. The first example presents how we can define, for example, the image of set X under relation R. So the func means that we are going to define functor operation. Again, R dot colon X, it is a notation way, the author can decide. We can use this symbol dot colon to represent the image. After this arrow, we declare the result type. So every image is a set. What means that for every Y, which is a object, holds Y belongs to it. It represents the image. If and only if there exists X being object such that ordered pair XY belongs to R, relations are binary relations in this case. So these are sets of ordered pairs. So this pair belongs to the relation, and the X belongs to our capital X. And for functors, we have to prove two conditions. First, we have to prove that there exists at least one set which in which this property holds, as in types. So, but also we have to declare the uniqueness. So when we define new operations, we have to prove that the result is unique. So if we have two sets which satisfy these conditions, definition conditions, then the sets are in fact the same set. Okay, and we have also another way of defining operations using equals keyword. So, for example, the first example defined the image of arbitrary set X, and in the second case we define image of one element. So again, we have relation R, object X, and a new operation represented by symbol im from image. We change format image Rx to write arguments. So the image Rx is a set, and it is equal to R dot colon singleton of X. So we can use the first definition in the second one. And when we use the equals keyword, conditions to be proven are different, because after equals we use already defined terms, so we don't have to prove that there exist such things and they are unique, because it was proven in the first definition. What we have to prove is just the result type of these definitions agreed with the result type declared after this arrow. So in this case, we have to prove in the coherence condition that R dot colon singleton of X is a set, but it is trivial because it was declared in the first definition. But even if the proofs are obvious or trivial, we have to use this word keyword, coherence. Okay, and now let's pass to structures, and I will show how to define structures and how to use structures. So structures are used to represent tuples, and in structures we can have arguments. So for example, we can define linear spaces over fields. So field will be an argument of our structure. Structures can have ancestors, and multi-inheritance is supported. So for example, when you want to work with topological groups, we can first develop topologies, define topology structure and facts about topology, and separately we can introduce groups and develop the group theory. And at some point we can merge all these theories into one, and we can define the new structure with two ancestors. Of course, we have named the new structure, and in structure we have a list of fields, and each field has a list of selectors and the type of selector. And in this example, we see the definition of B-module structure over two structures. So left and right module. So we take two arguments, and blue are predecessors or ancestors of our new defined structure. So we have module structure over first structure, right module structure. The names here are not symmetric in the sense the first one would be named left mod structure, but authors decided to use these names, and so such names are used, and B-mod structure merges all these left and right modules, and B-mod structure consists of the carrier and addition, zero, addition, which is a binary operation of the carrier, zero element, which is element of the carrier, left multiplication represented with L-mult keyword symbol, which is a function between Cartesian product to the carrier, and right multiplication, which is again a function between symmetric Cartesian product into the carrier. So it is just to show how structures look like, and how structures can be used. So, for example, when we want to define, let's say, I'm sorry, when you, sorry, okay, when we want to define the ring of integers, so we have to choose the appropriate structure, and it is example from the MML. So we have double loop structure, which is a structure consisting the carrier, two binary operations, and two fixed elements. So it is, this double loop structure is only structure of ring, and the ring of integers can be defined as a double loop structure, where the carrier is int. Int represents the set of all integer numbers. Added int is a function which represents the addition of integers. Mult-int is a function which represents the multiplication of integers. This one element, one f, the one is one understood as element of integer numbers, and similar with zero. Of course, these all notions, int, added the int, mult-int, in, and so on, must be defined somewhere in the MML. And in fact, they are. And so having such structure with these fields, we can put new name, let's say ring of integer, of int ring, and use these rings for further development. So this is, we call aggregates. And another usage are forgetful functors. Forgetful functors are used when we merge two theories. For example, as I said previously, we have topological groups. So we have a sequence of structures, like one sort, it is a root of structure. It is very simple structure with one set called carrier. Then we have a structure used for topological structures, for representing topological structures. So we have one set, the carrier and subset family of the carrier named topology. Magma, multiplication magma used for defining groups with carrier and some binary operation. Of course, mult magma is not a group, it is only structure for groups, and then we have to define some properties, of course, of the structure to make the structure being a group. And then we can merge topological structure with magma and define topological group structure with carrier multiplication topology. And we can, of course, ensure that operations are continuous in this structure. Yes, so of course we have to define some properties of this new structure. And here we can hit the top struct of G is strict, where G is a topological structure. So the strict means, the struct is strict means that it has only these fields which are introduced in the definition. So for example, topological group is not a strict group because it has also topology. And topological group is not a strict topology because it has also group part. But the top struct of G is strict topological. So there are cases when we want to have only strict parts of complex structures, and we can use forgetful functors for it. And last way of using structures are we call selector terms. So when we want to touch or to make reasoning about choosing field of a structure, so we can use the same. The 0f is the value of the structure. So similar to forgetful functors, but forgetful functors represents substructures, but selector terms represent just one selector. Okay, and how we can formulate facts in the Mizar system? So we have, let's say, two categories of facts. The first category consists of facts which have to be referred to when we want to use the meaning of fact. So when we have theorem or lemmas or scheme, we have to directly refer. So we have to, in some way, write that some fact holds by some other theorem. But we have also some facts. In Mizar text, we can define some facts using special constructions. And these constructions makes reasoning more automatic. So we have implemented several efficient algorithms to automatically some facts to verify some facts more automatically without direct referring to facts required for proving the new facts. And these automatic constructions, let's say automatic constructions, are reductions, factorial registrations, properties, and term identifications. And I will briefly show how to use and how they can be processed. Okay, and before this, let me say I will often use sentences like predicate formulas, qualified and attribute formulas. I mean, in Mizar we support three kinds of formulae. Predicative formulae, which are standard formulae, let's say n is greater or equal to 0. So using predicates. Qualified formulae. By qualified formulae, we understand the formulae where one term, an expression like mult magma, which is group. So the structure is term is type. And this kind of formulae we call qualified formulae. And the last is attribute formulae with syntax. Term, let's say, n is negative or non-negative. So attribute formulae uses adjectives after is, and qualified formulae uses nouns or types after is. Okay, and when we want to define or to prove some facts about introduced concept in definitions, we can use theorems. So we use keyword theorem, and we can formulate that image of X under relation R is included in the range of R. Of course, and between proof and end, we should place the proof of this fact. So theorems look like this with the theorem keyword. Schemes have different syntax. So it is an example of scheme of induction. So we use a keyword scheme. It is a name of scheme, its label. And for induction, we need one predicate over natural numbers. these not represent natural numbers. And after this colon, we define the meaning. So for every k being natural number, the property P holds, the P over k. Of course, provided the property P holds for 0, and for every k being natural numbers, if the property holds for k, it also holds for successor of k. Right, so we can declare schemes in this way, and of course we have to prove that this formula is true under these conditions. And so basically we have theorems, schemes. I said that we have also lemmas. Lemmas are just formulae with proofs, but without the keyword theorem. And lemmas are local to R. The difference between lemmas and theorems is that lemmas are local to the article, while theorems can be exported to the whole library. So it is only one difference in the sense of exporting of facts to library. And some theorems can be, or some facts can be written using other Miser constructions, and for example, reductions. So we can reduce terms to subterms. And the syntax is like we have register that for every R which is a real number, we can reduce the conjunction of R to R for real numbers, for complex not. And we have to prove, of course. And whenever Miser see this term R conjunction, then it will automatically reduce to R without explicit reference to the theorem. I'm sorry. And the limitation of usage reductions is that we can reduce terms to subterms. So for example, we cannot automatically reduce the difference of R to 0, because 0 is not in syntactic sense subterm of R minus R. Of course, they are equals, but 0 syntactically is not a subterm of the term R minus R. So this is what we cannot write in Miser text. Registrations, we have several kinds of registrations. One kind are, let's say, factorial registrations, which register that some term, in this sense, F, the image of finite set A under relation F is finite. So whenever A is finite, then the image is finite. So this is a syntax, and this factorial registration is processed automatically by Miser verifier. So whenever we have a finite and the function, Miser, without explicit reference to this fact, will understand that the image is also finite. So when we have some term and the attribute or a list of attributes after arrow. And conditional registration are used to make reasoning over adjectives without explicit reference to the facts. So this registrate cluster is just a keyword that we are going to register some property, and it means, this example means that every set which is infinite, the adjective before arrow, is also non-trivial in the sense that it has at least two elements, different elements. And we have really efficient and algorithms working with such registrations. So yes, okay. And maybe I can skip this, and okay. Another way of defining things are redefinitions. Redefinitions are very important. For example, we have defined inclusion. Yes, the first example defines inclusion between two sets, and it is expressed in the terms of membership of elements. So every X which belongs to A also belongs to B. But when the arguments of inclusions are, let's say, relations, then we can redefine the definitions from membership of elements to membership of pairs of elements, because the relations are pairs. So we can redefine when PR are not sets but relations. We can say that inclusion means that for every A, B being objects such that pair of A and B belongs to left relation, I mean P, then the pair belongs to the right relation, here R. So we can change, it is the same inclusion, but expressed in different language. The language related to the mathematical theory. So for example, inclusion of functions would be defined using domains and values of functions. And of course, we have to prove that all these two definitions, I mean, inclusion of sets, arbitrary sets and relations, are compatible. They represent the same concept, but expressed in different ways. And such redefinitions can be used in different proofs. And now I think we can see the first time the Misar proof, the first time during this presentation. And let me explain in more detail these two proofs. So when we want to prove that this tilde mark represents the inverse of relation. So if relation P is included in R, then the inverse of P is included in the inverse of the relation R. So the proof is enclosed within the proof block between proof and keywords. And how we prove implications in the classical way, we assume the predecessor. So we use keyword assume. A1 is a label of the statement. So we assume P is included in R, and we put the label for this statement A1. And now we have to prove the right side of implication. And because we would like to prove the inclusion of inverses, we can take an arbitrary object X, because of in previous slide we had that in inclusion we had for X being object. So we have this let. So let's take arbitrary X. And now we have to assume that this X belongs to the left term. So X belongs to the inverse of P, and we can put name for this statement A2 for next use. And what we conclude from this statement that X belongs to inverse, because inverse of relation is a relation, of course, then we can represent our X as a pair. So we can introduce new variables a and b such that our x is a pair of a and b. And we have to refer to some definition. We need this step. We have to decompose x into a pair of elements, a and b, because we want to inverse these elements, okay? And so if x is equal to a and b, to the pair a and b, then we can, and we know that this x, in the statement A2, we know that this x belongs to inverse of p, then we can conclude that pair BA belongs to P. Okay, so we inversed two elements. And we have to justify why this inversion is valid. So we refer to statement A2, A3, and definition of inverse. Relat 1 def 7 is definition of the inverse. Okay, and now, because pair BA belongs to P, and in the statement A1, we know that P is included in R, then we can conclude that BA belongs to R. And if BA belongs to R, then AB belongs to inverse of R by definition of relat 1. This thesis, keyword thesis, represents the current thesis of the theorem. So here it exactly means X belongs to the inverse of R. I think it is understandable. And the right proof is shorter in the number of lines, but this number of lines is not so important, but it is easier in the structure. Please observe the difference. In the left proof, we have let X. We took one object X, which was decomposed to A and B. And in the second proof, we could take two elements A and B, because here we applied the definition of inclusion of relations from the second definition, represented in terms of pairs. So we don't need an X which would be decomposed, but we can take two elements A and B, and we can assume that this pair belongs to the left inverse. Then we can inverse elements referring to the definition of inverse. Then because P is included in R, what is assumed in A1 statement, we can conclude that BA belongs to R, and then we can conclude that A belongs to B, AB belongs to the inverse of R. So again, this thesis means that AB belongs to R. So depending on which definition of inclusion we chosen, the proofs can be different. And all these two proofs are, of course, acceptable by the miser. So the authors can decide, let's say, in which language, in which domains the proofs will be written. This is, no, I can skip. So how we can justify statements in miser? We have three ways of justifications, like simple justification, proofs, and schematization. So the simple justifications use keyword by. So for example, we have some statement one with a label A, and we want to refer to the statement, so we can justify statement B by A. It is a simple justification using by. To the local lemma, and we want to refer to external theorems, external in the sense imported from that database, not proven in our article, but imported from database. we use again keyword by, then the file name of the external file and the number of definition of theorem. So Tarski :def1 means that we refer to the first definition defined in the article Tarski. So X belongs to the singleton of X by the definition. We can assume that it is the definition of being singleton. So simple justifications are simple uses by. Proofs are enclosed within proof and block. And we have several kinds of proofs. Because we have several connectives supported, we have several kinds of proofs. So the simple formula A, this A represents some formulae, doesn't matter what it means. When we have formula A, we can prove, these dots represent some reasoning, and we use keyword thus to underline that our goal is this formula A. So because we want to prove A, we have at the end thus A. Or in previous example, we could see the hence keyword, but hence is kind of abbreviation of thus and linking to the previous statement. And when we have conjunction of two statements, so we have to prove each element of the conjunction each by each. So we can have some reasoning. Thus, first conjunct, thus A. Then next reasoning, thus B. So when we have conjunction of 5 formula like A and B and C and D and E, in the proof we have to have thus A, thus B, thus C, thus D, thus E, and so on. In the order. So when we have A and B, we have to have thus A, thus B, not thus B, thus A. Implications can be proven following natural deduction. So we can assume A, and we have to conclude statement B. So assume A, reasoning thus B. When we want to prove disjunction, we can assume that first disjunct is not true, and then we have to prove that the second one is true. So natural deduction allows for such reasoning, and it works fine. So we assume that the first is not true and second is true. If we have disjunction, let's say A or B or C, we can assume that the first two are not true, and then we have to prove that the third one that it is true. Equivalence, if and only if, is represented as two implications. So first we have to prove that the first implication holds. So after proof we have thus A implies B, and then we have to prove the implication. So we can assume A and prove B, and then we have to prove the second implication, thus B implies A. So it is natural way of proving equivalence, understood as a conjunction of two implications. And also we support reasoning by ad absurdum. So when we have to prove A, we can assume that A is not true, and then we have to find a contradiction in our reasoning. So these skeletons are allowed. And if we talk about quantifiers, So for general formulae, for x being type T holds some property P, we can take arbitrary x of type T. So for we replace by let, and we have to conclude with the property P. So let does. For existential formulae, we have to construct some example with the type T, which satisfy the property T. And for existential proofs, we use keyword take. So we can take some x equal to some example, and this example should be constructed in some way in this reasoning. And then we have to prove that the property P holds for our example. And how to use schemes. Previously I presented the scheme of induction, and to prove that, for example, 2 divides the implication of 2 consecutive natural numbers, we have to define, we call it local predicate. So defpred defines predicate. Local in the sense it is not exported to database, but it's visible only within this proof. So we define some property P over natural number, which means that 2 divides the multiplication of 2 consecutive numbers, and $1 represents the argument of this predicate. So it is not n, it is the value of the argument of the predicate, of the argument of the predicate P. And first we have to prove that P holds for 0. Then we have to prove that if P holds for arbitrary K, then holds for the successor of K. And when we prove statements N and B, we can refer to the scheme of induction. So for K being not holds the property key from. So this in simple justification we use keyword by, but here we can use keyword from. So from the scheme of natural induction, which is represented, which is the second scheme in NAT article. Okay, it is just the recalling of the scheme of induction. I think I have half an hour more, so maybe let's skip this example. When I have time, I will come back to this example. But let me say a few words how to install verifier and other topics. So the MISR, the MISR system can be downloaded from our website, http://misr.uwb.edu.pl system index, and the MISR system is supported for several platforms: Windows, Linux, MacOS, and several others, and it can be freely downloaded and used. So first we should download the system from our homepage. The installation is pretty easy, but so first we have to unzip the downloaded file, and for example we can unzip to the root of C hard drive to this library, and we have to remember about fixing two things. We have to add the installation folder to path variable. So when we install in C MISR folder, this folder should be added to path environment variable. And how to add depends on the system. In Windows, in Linux, in different ways. And again, the important thing is we have to set the environment variables with the name misfiles and the same name. We should put the same name to misfiles directory. To misfiles, sorry, environment variable. So these two things should be used. And to write Mizar articles, we can use arbitrary plain text editor. Even Notepad can be used, but it's not very. It's possible to use, but we don't recommend, of course, to use Notepad. We recommend using Emacs because there are several automations for processing implemented in Mizar. So the Emacs can be downloaded from the Emacs homepage, and I recommend this version. There are newer versions of Emacs, but we found that there are some incompatibilities. Some syntax of Emacs files changed, and the newest version may not work with Mizar properly. So we recommend this version or older one. And to merge Emacs with Mizar or Mizar with Emacs, we should copy one file from Mizar distribution directory .emacs to home directory or to the root of C. It depends on your system. So the several steps should be done for installation, and in distribution folder of the system you can find several files and subfolders. So the most important subfolders are ABSTR subfolder. It contains abstracts of all articles. Abstracts, not in the sense of mathematical papers when we describe the content of the whole paper, but abstracts in our sense are files. We remove proofs from original Mizar papers and we call them abstracts. So in abstracts we have formulations of all definitions, theorems, schemes, and so on. In the folder MML we have full Mizar articles with all proofs. So whenever we want to find what is proven in MML, what, not how, we can look at abstracts. They are shorter, easier to read. But when we want to look at proofs and we want to know how some things were proven, we have to look at whole articles stored in MML subdirectory. And folder prel is very important, but very important for system, but not for authors, because internal representation of database is included there. So authors never look at these files. And the most important files are ini, MML ini. It is the number of current version. We issue several versions a year, and when we look at our homepage, the one version is named as an official version, but we issue new versions when new articles are submitted, are added to MML, and so quite many versions can be found there. And in MML ini you can find the precise numbers of your versions. MML lar is a file with the list of all file names of all articles. So whenever when user uses Mizar for writing articles, it is not important, but when some researchers would like to process Mizar articles for some reasons, for example, for representing in its own format or in the internet, and the order of processing of files is important, then it can be found in this file. MML VCT VCT is a list of all symbols introduced MML. You can look at this. I mean, authors can look at this if he would like to know about all symbols. Mizar DCT is a list of all Mizar reserved words like theorem, scheme, and so on. And Mizar MSG is a list of all comments of errors. So during verification process, the verifier may refer some errors, and it puts some marks into text and comments in English what this error means. Okay, and when we want to verify our article, we should call several programs or batch file. So for verification, as maybe you remember, verification consists of two stages: accommodation, which reads environment and imports data from database to our article. So the program name is accom, and we process file name placed in the subdirectory text. So we propose, and we usually work with our working directory. We create subdirectory text and put all Mizar articles into this text subdirectory. So we accommodate our article, then we can verify. So verifier is the program name of our main verification tool. So we verify our file from text subdirectory, and the verifier creates some internal files, and to put flags of errors into original article, we can or we should call another program rflag. So the loop of processing accom verifier rflag, accom verifier rflag. Of course, it's not. Instead of using these two programs, we can call one batch file misf, which calls internally all these required programs. So instead of calling accom verifier rflag, accom verifier rflag, we can call just misf text file name, and it calls all required programs. So I recommend to use this red comment for verification. And when the article is finished, we can export to database, local or database, to develop next articles. So we should call these two programs exporter and transferer, which prepares our local database. And again, instead of writing these two programs, we can call mis2prel batch, which creates local database, and we can generate our abstract of our articles. So mis2apps can generate or generates abstract part of our article. And how the verifier is built. So the main program verifier consists of several modules. And the first module is named parser. We call it, it is typical name parser, which verifies syntactic of our articles. So checks whether we use correct words, where all brackets opened are also closed, and so on. And build a parse tree of our article. And for ordinary users, it's not important, but for people who would like to work with Mizar, not only for verification, but for other purposes, this parse tree is stored in WSX file. So maybe some be interested in it. It is XML-based file. So after parsing stage, the next module, variables identifier, is called, and it identifies all used variables and labels. In Mizar proofs, we allow using variables with the same names at the same level of proof. So in one proof, we can have several variables named A. Of course, they represent different variables, and they hide one can hide another one. So Mizar verifier has to precisely know which A is which. So it identifies and internally represents by consecutive numbers. And the information is stored in next XML file. And the analyzer, the third module analyzer, is very important, quite complex module, which identifies, makes disambiguation of all used symbols. And as I said at the beginning, because of overloading, one symbol can be used for many notions, and plus is used for almost 200 different notions in MML. So analyzer identifies which plus is which based on the types of arguments of notions. And the next module is reasoner. Reasoner is a module responsible for verification proof structure. So it checks if you for example, try to prove implication. So the reasoner checks if we correctly assumed the predecessor of implication and try to prove right part of implication. So reasoner verifies structure of proof, and then checker verifies the logical correctness of our proofs. And the checker consists of several submodules. The first one is pre-checker, which works at the logical levels. So the pre-checker negates formulae. As I said, Mizar works as a disprover. So the pre-checker negates, disprover computes the disjunctive normal form of inference, and prepares things for next modules. And each disjunct in disjunctive normal form is verified separately. So from one inference, we can have several disjuncts. And usually we have several disjuncts. Equalizer. Equalizer is a module which processes the equational calculus. Equalizer collects all equalities accessible at a given stage of proof and computes congruence closure over all accessible equalities. And the sources of these equalities are various, for example, reductions, as I told previously, or equals constructions. It was seen at our examples previously. And after computing the congruence closure of equalities, the unifier, the last the last module which unifies formulae. And when some gaps are found by verifier in proofs, then errors are reported and authors must fill the gaps and call verifier again and again and again. And what is important, the meter, there are systems which work until the first error. So when the first error is met, the system stops working and ask sorry, I get some chat and okay. Apart the main verifier program, we have several other tools which can clean our proofs, clean in various senses. Some tools can clean proofs and some can clean environments. And for example, RelPrem. RelPrem is a very useful tool which marks irrelevant references. So for example, when we have one proof step and we can, in measure text, I mean, we can say that this statement holds by A, B, C, and D lemmas. But in fact, let's say A and B are not needed to prove our statement. Verifier accepts statement, but RelPrem can mark that some of references can be removed from our proof and the proof is still correct. So it is very useful tool. Checklab is simple tool which marks unused labels. So we can mark each label, but each statement we can mark, but we can use only several labels and we can remove, or Checklab can mark unused for us. INATS in ACC marks unused blocks. This very useful tool. When we have long proof, sometimes we write proof, write, and at some point we change our mind and we want to formulate different proofs and formalize different proofs, and old proofs are left in our article. And INATS can mark let's say old proofs, unused proofs, or sub-proofs for us. Relators marks irrelevant iterative steps in iterative equality, and reliever can marks steps which can be cancelled and merged and cancelled, and such works can be done. And we can clean our environment by marking which vocabulary files or theorems files shouldn't be imported to our new article. So this simple cleaning of articles. And important part of our project is our journal, formalized mathematics. Formalized mathematics, and this journal was established in 1990, so even before Wikipedia was established, and it was pioneering journal in the field of formalized mathematics. It was published on the internet also. In this paper, we published abstracts and simple proofs of Miser articles contributed to the Miser mathematical library. And these papers are automatically generated from MISR articles. It is very important that author can write MISR article in the MISR language, and then we can prepare LaTeX papers and publish in formalized mathematics. In these articles, we can change the representation of symbols. So in MISR article, it is a plain text. So for example, we cannot use symbols sum or product as we can see in traditional mathematics. I mean sigma and pi, for example. But during this translation from MISR article to LaTeX format, we can declare how symbols from MISR paper can be or should be represented in LaTeX format. So we call some format patterns for representation, and the papers published in formalized mathematics look like mathematical papers using all mathematical symbols accessible at LaTeX. And this journal is issued quarterly by De Gruyter Sayendo, and the link is visible. It is indexed in several abstract services or paper services, mathematical and computer science. I think the most important is Web of Science, DBLP, and many, many others. Of course, we have DOI for it, and the homepage of the journal is fm.misr.org. And it would be really nice to have, would be really nice to have some contributions from you to this journal via writing MISR articles. And the short list of inferences, of course, there are many papers about MISR, but these three are most general and news about more general informations about the MISR. The first one, MISR state of the art and beyond, describes the system. The second paper, the role of the MISR mathematical library, describes MML. And the last one, MISR in nutshell, it is quite old document from 2010, but it is many examples are presented there and ways how to use different constructions. It is not very up to date because the MISR system is still under development, and we introduce new constructions. But this paper is quite good for beginning to start writing MISR articles. And I think my time is almost over. So at the end, the MISR homepage is here. We have an email service, MISR user service, for questions about all topics about MISR system, MISR, how to formulate, how to use system, and how all topics related to the MISR system can be asked using this MISR user service, or you can write directly to members of the MISR group, to me or to my colleagues from my laboratory. We would be very glad, very happy to help you, and all questions, all ways of cooperation are very welcome. As I said at the beginning, I believe that it is the first seminar, but not last, and please think about longer cooperation between our laboratories, our projects. And I think thank you I think I should stop now. Thank you very much for listening this lecture. And I understand that we have a break and then exercise session and questions answer off. If you have questions now, maybe you can ask. So thank you very much for listening.
Okay, thank you so much, Professor. That's very interesting. Yeah, thank you so much. Maybe you may take a break for a while, and we will have the break for 30 minutes until 3:30 GMT+7. And for participants, if possible, please stay in this meeting. Yeah, you can turn off your camera and also your microphone. So yeah, see you and take your break.
Okay, thank you. See you in half an hour.
Okay.
Hello, I am ready.
Okay. Yeah. So again, good afternoon, everyone. We are back here. So yeah, I hope the break refreshes us. So we will ready for the next session. So we will go to the second topic, the second subtopic of Professor Kornilowicz's talk. It is about working with Mizar. So Professor, you may start your second session now.
Yes, thank you very much. I have a question. Should I type my Mizar exercises, or would you like to type on your computers? Are you ready with your computers or not?
I think some of them are ready, but
so I understand it is better I would type and explain step by step. Okay?
Yeah, it's really
okay. Okay, I'm ready for it. So I prepared very simple exercises about relations, similar examples which I presented in this lecture, and I will type step-by-step proofs, and I will make several mistakes and try to fix them. Okay, so please don't complain too much on my mistakes. Okay. So okay. I would like to share my screen. Okay, can you see this screen?
Yes.
Is font big enough, or should I make it bigger?
I think it's enough, Professor.
Enough, okay.
Yeah.
So I would like to show you how to prove how to use Mizar verifier on very simple examples about relations, and examples on chat. I will send a link to PDF with examples, okay? But I will stop sharing for a while, so I cannot open. Okay. Okay, I put a link to exercise files on the chat. I will. Okay. So first, the first example I would like to show is, can you download the file? Or if you like.
Yeah, it can
Maybe
be
it's not
downloaded.
important, but I will. Okay, P included in R, tilde equal to R, tilde composed with P R. Okay. Do you see PDF file or my Emacs text?
Emacs, I think.
Emacs, okay.
Yeah.
So for a while I will share my PDF file. Which one it is? This one. Okay. So our task for this exercise is using the following definitions. So the equality of relations defined in terms of pairs. So it is the second definition in Relat 1 article, and the definition of inverse of the relation. So the seventh definition in Relat 1 defines inverse of relation, denoted with tilde symbol, and the decomposition of relation. It is 8th definition, and domain of relation is defined as a synonym of projectivity operation, and codomain is a synonym of second projection of X. We would like to prove the, the following 5 theorems. So the theorem number 1 says that the inverse of the composition of two relations is a compositions of inverse of composition of two inverses, right? It is mathematically easy task. So first, I prepared environment file for this operation, and in environment part we have to declare what things we would like to import from database. And we can see several directives: vocabularies, notations, constructors, definitions, theorems. And I will briefly say, just briefly, what concepts are important using these directives. In vocabularies, we have to put vocabulary names from which we would like to import just symbols without any meaning, just symbols, just new words. And of course, how to know in which vocabulary symbols are introduced. We have some tool named FindVoc, which helps us. What I can say, when we start to learn a new system, either new proof assistant or programming language, I would say that language is easy part to learn. The biggest problem with learning new tools are their libraries, because of their size or ways of writings. So I would say that Mizar language is easy to know, and I believe it is readable for mathematicians. But the problem is the knowledge about library. We have more than 1,000 articles with many concepts, and how to know what is formalized and how and where it is placed. So for the moment, I would like to focus on how to prove things, and I will import things without deep explanation why I used these declarations, because I need quite much time to say about environment part. Just briefly, in vocabularies we import symbols from database. In notations we import ways of writings of different concepts. I mean definitions of predicates, adjectives, which we would like to use in our articles. And constructors, in constructors we import, I would say, the meanings of all notions. And in principle, notations and constructors, in these two directives, we should import the same things. But as you can see on this example, it is not true in 100%, because the list of constructors is longer than the list of notations in this short example. When I have time, I will explain at the end, but if not, we will skip maybe for next meeting if we have such opportunity. In definitions, directive, we import so-called definitional expansions. The sense we import possible ways of proving our theorems, according to which definitions. And in theorems, we import file names from which we would like to use already proven theorems. Okay, so it is environment part, just briefly. The text proper or proper text of definition, we start from begin keyword, from this keyword, and first we can reserve some variables for types. So instead of formulate theorems like for every P being relation holds, for every Q be relation holds, and so on, we can reserve P, Q, R or more variables for relation, and then we can use these variables as variables representing relation in theorems. So our theorem can have such concise formulation. Inverse of the composition is equal to the composition of inverses. And now, okay, I can verify this article. So in the Emacs, we have Mizar menu. We have run Mizar. Okay, so Mizar was run, and these red or brown comments are added by the verifier. Comma, comma, arrow is a start of beginnings of line with errors, and star 4 means error number 4. With explanation, this inference is not accepted. This error means that Mizar doesn't say that it is not true. Mizar says that I cannot compute that it is true. You should give me, you can give me a proof, a justification of this statement. Okay, so number 4 means that more detailed proof is required by the system. Before I start writing proof, let me make some errors. Okay, I will comment reservation block. So these two commas starts the comment, and now I will verify the article. So Mizar menu, Mizar run Mizar, and look, we have many errors, numbers 140 with with explanation unknown variable. It means that we used variable p, but means we didn't introduce this variable. Okay, and the same with r and other things. So I uncomment the line, I call verifier. Instead of clicking menu Mizar and run Mizar, I can use some shortcuts on my keyboard, and I will use rather this way of verification. Okay, so when we know what PR are, let's cancel the P. I verified, and again we have some errors. 172 unknown functor format. It means that there is something wrong with the text. In this case,
pardon me, Professor.
Yes.
I think you share. You still share the PDF file.
Ah, really?
Yeah.
I'm sorry. I'm sorry. And now, Emacs?
Yes.
Emacs, okay.
Yeah.
Okay, let me. I thought about some errors, so let's quickly, okay, and I canceled or commented the line with introduction of variables PQR and called verifier using Mizar, menu, run Mizar, okay, and these errors are reported. It means that unknown variables P and R were never introduced in this article. So when I uncomment this line with introduction of variables PQR and verify article again, okay, error number 4 is reported. Error number 4 means that please justify this statement. Mizar doesn't say that it is not true. Mizar says, I cannot compute, I cannot verify this. Maybe you need some proof or justification, okay? So to write the proof, we start block and proof, okay? And we will put proof here. I will verify this file, Mizar, run Mizar, and I have another error number 70, with the statement something remains to be proved. It is clear proof is empty, and I have to put my proof inside this proof block. And we are going to prove equality of two expressions, right? We would like to prove equality our two expressions. Our expressions, left and right, are relations, because inverse of relations is relation and composition of relations is relation. So I'm going to prove this. I'm going to prove this fact following the equality of relations. And when now I'm looking for the definition of equality of relation, I know that this equality is defined in the article named relat1. So I would like to go to the file with the name relat1. And here we can see the whole article about relations. So we have some comments and copyright at the beginnings, then we have some environment part, then we have the article, and okay, here we can see the definition of equality of relations. Okay, so relations are equal what means that for every A and B, pairs belongs to P, even only if B belongs to R. So I would like to follow this structure of the proof. So to prove the equality, I have to prove this general formula. So I am going back to my file, and in the file there was written for A and B holds. So when we prove general statement, we can fix variable A and B. Because for A and B, with let A and B semicolon. And I verified the article, and the verifier said, oh, there is something wrong. I don't know what A and B are. So A and B, I have to declare types of variables. I can do it in reserve block, but I can do also here. So I can say that let A and B be, and I have to know what type of A and B should be. And look, here in the article, there is no type written close to A and B. So I have to look for the whole article, the original article, and here I can see that A and B I reserved for arbitrary objects. So I have to I have to type this. I have to type this name of the type of variables A and B. Okay, so my generalization, let statement generalizes to two variables. We fixed two variables A and B, and what is the next part of proof? So let's go again to the proof of to the definition of equality. So general formula we had for A and B holds. So we fixed two variables, and now we have to prove this equality, this equivalence, right? If and only if statement. And so now my thesis is, does A, thesis means the part which left to be proven in the article. So pair AB belongs to if and only if the same pair belongs to the right part of the equivalence. And now I call verifier, and look, we have two errors number 4. These two errors number 4 means again, Mizar doesn't understand that it is true. I have to give proof. Why we have two errors? Because equivalencies are conjunctions of two implications, and for each implication, one error is reported. So so now we are going to prove this equivalence, right? How to prove equivalencies? Equivalence is a conjunction of two implications. So first, I have to prove first implication, and then I have to prove the second implication. So it means that I have to prove such two implications. And when I verify Mizar, when I call Mizar, I still have two errors number 4, but they are reported close to implications. Is it clear? I think if you have questions during my presentation, you can ask. You can interrupt me and ask. Yes.
Okay.
Yes.
Actually, I'm running the Emacs now, but I have. Can I share screen to show you the?
So I will stop my sharing. Okay.
So, yeah, I have 55 error for here. So what does it mean actually?
Yes, you have 55 invalid generalization. Why you used this let statement? Because you are going to use equality of relations, and you should expand your environment part with definitions. So go to your environment, add new directive, definitions.
Okay,
the order is not important. Definitions as definitions. Okay, relat 1. All file names should be written in uppercase letters, semicolon. And now
I can run wizard.
Yes. This expanding.
Okay.
So you imported the definitional expansion.
Okay.
Okay.
Yeah. Thank you.
Just, building environment, it's not so easy task, you know. And I think today it's better to focus on proofs rather than on buildings of environments. Environments can be copied somehow from different articles, right? And okay, is it clear now?
Yeah, it's clear. Thank you.
You're welcome. Okay, I will share my screen again. So now we are going to prove these two implications. I will switch the order of implications. I just moved one. And look, I have another error, 51. 51 means invalid conclusion, because the system was expected implication, but opposite direction, right? The order of, in equivalence, we have alpha implies beta and beta implies alpha. And in this order, we have to place the implications. So now I put these two implications in a good order. So what we have to do, we have to prove this implication. So I can open new proof block, okay, and prove implication inside this block. So how do we prove implications? We assume left part. So in this case, it is pair AB in PR. Okay, we assume this, and thus our thesis, I mean the part of proof which left to be proven. Okay. Okay. I have some error 52. Invalid assumption. Can you say what is wrong in this assumption? What is wrong in this assumption? Look,
yeah, it's R. It's supposed to be R.
Yes.
R.
Yes, this Q, right?
Yeah.
In here, it is composition of P and R, but I assumed that the composition of P and some Q, right? And Mizar didn't agree. with me. So I have to change Q to R, verify it again. So assumption is correct, and my thesis, current thesis, is left to be proven, right? So Mizar says that I have to prove this statement. Correct? Correct. So how to prove? How to prove? From this assumption, we can conclude that because pair A and B belongs to the inverse of relation, then pair BA belongs to the relation P and R. Right? It should be true, because the inverse operation reverses elements. And I verified, and look, I have error number 4. It means that I have to justify this statement. So why BA belongs to this? It belongs because of the property of the inverse. So here I have to refer to the definition of inverse, and go to Relat 1, where the inverse is defined, and it is 7th definition in Relat 1 article. Here we can see that the xy belongs to it. It means inverse if and only if the opposite pair belongs to the original relation. So now I have to not here here I have to refer to the definition of inverse. Yes, I missed Relat 1. Sorry. Okay, I did mistake. It is relat, R-E-L, relat, but I switched letters, so I have to write it carefully. Okay. And this inference is accepted by verifier. So again, let me comment this. Without this reference, I have error. Just Miller says, please prove it, justify it. So I claim that this step is correct because of assumption. So this then keyword refers to the previous statement. So because AB belongs to the inverse, then PA belongs to the original relation by property of inverse operation. So now what we can do now? We have to use the property of composition of two relations, and let's go to Relat 1. I found the symbol star. We use star for the composition of relations, but it is a synonym of composition defined using this symbol: bracket, hash mark, and bracket, which is defined just several lines upper. So this definition describes the composition of two relations. And what is the meaning? Pair xy belongs to the composition if and only if there exists another element z such that pair xz belongs to the first element and zy belongs to the second element, second relation. So we can put this z in this z, we can put this z in the middle of this pair. Okay, so we can decompose this pair into this into two other pairs, and because some pair belongs to composition. There exists something, and now we consider, because we know that there exists some Z which satisfies some property, and we need this Z for our reasoning. So using the keyword consider, we can introduce this Z to our proof. So there exists Z such that, so I have to type this, property. Okay, such that AZ belongs, yes?
Can I ask? Yeah,
Sure.
it's supposed to be Z, a Z, or it can be like the other letter, like C, D, and so on.
Any new symbol can be used.
All right. Okay.
Let's add 5Z. Okay.
Okay.
Okay. In P, in R, right?
Yeah.
So, because we know that there exists something, we can introduce this something to our proof using this construction, consider, okay? So consider introduces new variables such that, and I copied these properties, verify, and again, what this is, okay? Z was never used before, so I get to type the type, I going to present the type of this variable. So what Z was in the original definition? No type here, right? So I go to reservations, and in this reservation block, there are no Z, okay? So go to, and here I can see that Z is reserved for objects, okay? So I must type object here. And what happened? Number 4 means that Mizar does not agree that I can introduce this variable Z. So, but I'm pretty sure I can do it. But look, I have to refer to the definition of inclusion, or of composition, sorry. So in this okay. In this step, I referred to the definition, but still I have error number 4. What is wrong here? Look, in the line above, I knew that per BA belongs to R. So here I swapped variables A and B. Here I should have B, and here I should A. And now the error disappeared. Because I can put Z between B and A. Right, let's go to the original definition. We have per X, Y. So first we have X, Z, and then Z, Y. And Mizar controls everything. Correct? So I cannot change A to B just for play. Okay, let me use Z instead of Z, okay? And now, what we can conclude? Look, our goal is to prove that pair AB belongs to the composition of two inverses. So what should be proven first? We can conclude this statement. Having In composition, we need third element. Okay, maybe it's better to A3. We have labels. Consider that such that we can label each formulae and what we can infer from statement A2. Because BZ belongs to P, we know that ZB belongs where? ZB belongs to inverse of P, right? By statement A2 and definition of inverse, that is def 7. Correct? Let me cancel A2 reference. Mizar does not agree that ZB belongs to P inverse. Why ZB belongs to P inverse? Because BZ belongs to P. So I need A2 at this place. Correct? And from the statement A4, what I can conclude? That because ZA belongs to R, by the inverse operation, we know that AZ belongs to R inverse by, again, A3 and relat 1 def 7. 7 definition of inverse. Right? No errors here. Let me try to write 8 instead of 7. Error number 4 is reported. So Mizar does not agree that it is true because of my mistyping. And now what we can know now. Look, maybe I can switch these two steps. Because AZ belongs to R tilde, R inverse, and ZB belongs to P inverse, we can conclude that pair AB, the first and the last element, belongs to the composition of these two relations. So, and it's our last goal. So to prove our last goal, we have to refer to the previous two statements. So let me name them like this. And my thesis holds by A4, A5. Number 4 still remained. What is missing? Can you help me? What is missing? In this step, in this inference, I would like to use the property of the inverse operation. So I have to refer to the definition of, not inverse, composition. In this step, I would like to use the property of composition of two relations. So I have to refer to the definition of inverse. And look, in this, no errors inside this first implication. It is proven.
Mr. Artur.
Any questions? Yes.
Okay, so I think it's quite challenging to do the proving using the Mizar, right? So my question is, for example, we just have the theorem and then we are going to do the proving. So do you have like the suggestion for us to, so for example, what we need to do first? Like, okay, so we have we are going to prove, for example, we are going to prove this theorem. So because before you already explained to us, oh, you have to prepare about this. So for example, we are the new one that are going to do the proving. So what we are going to do to prepare first?
Several things in parallel, I would say. Of course, we need to learn language. We have to know how proofs can be composed, the structure of proofs. So these skeletons of in the lecture I presented skeletons of different kinds of proofs. Conjunction has different structure of proof than implication, right?
Yeah.
And also we should know the library, how definitions, what is already in the library, how it is defined. So several things should be learned in parallel.
Yeah.
I know it is difficult. I know.
Yes. So, for example, sir, for example, I have this one. So, because now I'm doing my research about this one, and then I'm doing the proving. So I have like some difficulties in doing the proving. So the thing that come to my mind just like, oh, first step, I just do the proving by myself in written, and then I have to find like the words that that I need to go to the environment, and also check again the proving, what is the definition or the proof, just like what you said before, that the theorem are parallel. And then but I'm still have a problem in that thing, because I think it's quite hard to know what's the theorem or what the definition that already on the MML, and then yeah, that's it.
Yes, and you know, we have 1,400 articles more.
Yeah.
More than 10,000 definitions. How to know everything?
It's hard.
It's hard. It's really hard. So we have some tools like MML query is an internet service, maybe which can help to find what is proven and where. So maybe at the end I will show how to use this tool. I don't use it too much, but I can recommend for using for new persons, new in Miser, I mean. So should I continue the proof of this fact, or?
Yes, just continue, sir.
Yeah. Okay, and so the first conjunction, the first implication is proven, right? So now we have to prove the second implication. So again, I open the proof, new proof, log, and here we are going to prove implication, right? How do we prove implication? So we assume that AB belongs to left side, and we have to conclude with this state. Okay, I verified. There is a misprint here, 149 unknown predicate format. So I can, and what is inside the proof, we call it proof skeleton of proof. Skeleton means that the structure of proof is correct. I assumed what should be assumed. my goal, I know that my goal is correct. Okay, so let's change this P to Q again. MISA reports that assumption is invalid. Okay, so it means that the structure is incorrect. I assumed what shouldn't be assumed. So let's go to the correct form. And now I have to prove it. So because of my assumption, we assume that some pair belongs to the composition of some relations. So because then, referring to the definition of composition, I can introduce some Z object such that what A, B belongs to left argument of composition and not AB, AZ, and ZB belongs to the right argument of the composition. Number 4 still remained. So I have to refer to the definition of composition. Again, lat 1, def 7. Not the 7, def 8. So I don't remember names, okay? I can try 7, 8, and so MISA accepted that my pair AB can be decomposed. So now what we can do? Because A and Z belongs to the inverse of R, it means that ZA belongs to R by A6 and definition of the inverse. Accepted. And now in A7 we know that ZB belongs to the inverse, so we know that BZ belongs to P. By what? By A7 and again relat 1 def 7, definition of inverse. And now what we can see? What we can see from these two statements. Maybe I change the order, it's not important because they are not related each other. No, because BZ belongs to P and ZA belongs to R, and this Z is common in pairs. So from these two statements, I can infer that BA belongs to P composed with R, right? Verified. Error number 4 means that I have to refer to these previous statements. So I put names to these statements and I refer to these previous statements. And I suppose the error still remained. Why? Because I have to refer to the definition of composition. And now this inference is accepted. And because B and A belongs to P composed with R, what we can conclude? We can conclude what we need, that the reversed pair, I mean A and B, belongs to the inverse of this relation. So I can put name to this statement and I can use this A10 label in this inference. Error remained because I have to refer to the definition of the inverse. I think it is one of the most common errors by people who start learning MISR. Many people forget to refer to the definitions. Many people, our students often forget to refer to the definitions. Okay, I commented definition, I have an error, I refer to the definition and error disappeared. Error disappeared. So in this, I think mathematically easy task, right? That the property, one of the basic properties of the inverse and composition of relations, many MISR things should be used, like definitional expansions, skeletons of proofs, disconsider construction is very useful when we know that there exists something, some variable which satisfies some properties. We can introduce this variable to reasoning. So disconsider. Of course, it should be proven by some sources of why it is proof. Now I would like to prove similar theorem about composition, and I would like to we should stop at 1 Polish time, I mean 5 Indonesian time?
Yes, at 5 p.m. here.
5 p.m.?
Yeah, here. So maybe 30 minutes.
What time? Please tell me, or write on chat. What time should I? Okay. Okay, thank you. So the second example would be like this: that the composition of relations is transitive. Associative, sorry. Associative. Transition is for predicates. Okay. So I formulated new theorem, new task. So MISR asked me to prove this. So I opened the proof block. And again, because I'm proving the equality of two relations, because the composition of relation is relation, I can follow the same proof structure. So I can fix two variables, and now I have to prove two implications, right? So first implication says that if A and B belongs to the first relation, then it implies that the pair belongs to the second relation. I verified, so we can observe that this implication is marked with error number 4, but one more error occurred. We have one more error. 70, something remains to be proved. We have a comment. And what is this something? This something is the second. This something is the second implication, an opposite implication. So this statement should be proven. I verified and I have error number 4. In some sense, error numbers 4 are nice to have. Why? Because when we have errors number 4 means that we use correct words, we use correct proof structure. We need to prove it, we have to justify the statement, but everything is formulated in a correct way. So, for example, yes, I did some mistake about it, so I don't repeat it. So what we have to do? We have to prove these two implications separately. Again, I can open the proof block for the first. What we are going to prove inside this? We would like to prove this implication. So how do we prove implication? We assume left side and our goal is the right side of the implication. Correct? Correct.
Mr. Artur, can I
Yes.
ask, what is the difference between be and being for the using of
Be and being?
Yes, for this.
They are synonyms. Just
okay. So,
but when it is, we think that when we say consider that being, it more English, but let A be object.
oh,
But here I can put being as well.
all right.
But some people think that B is better, considering English language.
Yeah, thank you.
So for me, both are acceptable in any situation, just synonyms. We are not English native speakers, but many people think that it is more English. I have chat. Okay, so I will 45 minutes more. Okay, thank you. So let's go to our proof. So now we have two compositions, right? P and Q and R. So first, what we can do first? Because of the composition, we can introduce new variable. Consider C being object such that what? AC belongs to P composed with Q, right? Because we have P and Q and R. So this and per CB belongs to R by definition of not 7, 8 definition of composition. But in an A1 statement, we still have the composition. So we can decompose per A and AC. So because of A1, we can consider some D, new variable, being object, such that what? A and D belongs to P and DC belongs to Q, correct? By what? By A1 and relat 1 def 8. Yes, it is correct. No errors reported when I verify article. And I think that some of you could ask me why I wrote then consider C, but I didn't use then consider D. So let's try to use then here. And I expect we will have some error. Yes. Error 164 means nothing to link. Nothing to link. I said that then keyword is a link to the previous statement, but what is the previous statement to this statement? The previous statement is this one, right? The whole construction consider, and we cannot link to consider constructions. So this then is not allowed here because it is not unique, it's not well defined. Because in this consider we have several formulae, A1, A and 2, and possibly 3, 4, and so on. And to which of formulae then would link? To the first, to the last, to all of them? So we don't allow to link to consider constructions, but instead of it, we have to use labels. So this A1 links to this statement, refers to this statement. Okay, so I think we have decomposed all pairs, and now we have composed something. We have to prove that AB belongs to this composition. So to prove that AB belongs to this composition, we have to know that A something belongs to P and something B belongs to this composition. So our candidates are, we have 4 statements here. We have to play with these pairs in some way. So which pair of elements would belong to this? You composed with which one? Oh, look, A4, DC belongs to Q, and A2, CB belongs to R. It means that D